So in 1959, the first plans were made for the H3 Interstate Highway to become the third Trans-Koolau traffic corridor. And in 1965, the state held its first public hearing on the H3 freeway proposal. The population growth of Windward Oahu put a major strain on both the Pali and Likelike highways, which had long been operating at capacity during rush hour. Traffic studies predicted that at least 1/3 of all Windward traffic would soon be heading for jobs and recreation in the airport, Leeward, and central Oahu areas. So H3 planning moved forward. Over the years, plans changed as citizen input and necessary environmental and other studies were taken into account. The final route chosen was from near Halawa Stadium into North Halawa Valley, through the Koolau Mountains to Haiku Valley, and from there to Kaneohe. Design for the tunnels began in 1987. Since these tunnels were part of the federal interstate highway system, they had to meet high standards. These included how steep the road could be at any point, how many lanes there had to be, how wide the shoulders should be, what kinds of air standards had to be maintained in the tunnels, and so on. One of the first things the tunnel designers needed to know was what kind of materials they'd have to deal with in building the tunnel. The tunnel had to be drilled through rock like this. It's called Koolau basalt. Koolau basalt is composed of 2-million-year-old lava flows. Some of this rock, mainly the portion near the Halawa end of the tunnel route, was very weathered and much softer than the rest. The designers were also concerned that in building the tunnel they might encounter water, which is thought to be present under high pressure. But only where it's trapped between impervious geologic dikes on the Koolaus. In order to get a better idea of what they might be up against, the designers had a 14-foot diameter, 1-mile-long exploratory tunnel dug along the route that would be followed by the main tunnels. This work was done between February and December of 1989. The exploratory tunnel confirmed the assumption of the designers that the elevation chosen for the tunnel would be above the level where substantial water would be encountered. That confirmation, plus the increased data on the hardness and layering of the rock the tunnelers would go through, gave contractors the knowledge they needed to bid accurately for the main project, and saved much time and money in the long run. The project includes 2 main tunnels, or bores, one carrying traffic inbound to Halawa and the other carrying traffic outbound to Kaneohe. Since the tunnel route curves as it goes from one side of the mountains to the other, the tunnels are of slightly different lengths. The inbound tunnel is 4,890 feet long, while the outbound tunnel is 5,165 feet, almost a mile long. Each of the tunnels is designed for 2 lanes of traffic, with a breakdown lane for disabled vehicles. There are also 10 cross passages between the tunnels. One was built about every 500 feet along the tunnel route. These smaller tunnels can be used to get from one main tunnel to the other, for evacuation if need be, but they will also be used for electrical substations and equipment storage. In order to build the tunnels as rapidly and efficiently as possible, the work was divided between 2 contractors, one of whom started drilling from the Haiku portal and the other from the Halawa portal. Because the tunnels had to go through 2 different kinds of rock, 2 different excavation methods were used. On the Halawa side, the lava had weathered extensively over 2 million years and it ended up as very soft rock, which geologists call saprolite. Saprolite looks like this. It has the structural strength of hard clay, which isn't much. When it gets wet, it turns silty very quickly. So at the Halawa portal, initially the crews were able to dig the tunnel using backhoes and light-duty road header type mechanical excavators. As you can see, basically they just ground the rock away with a rotating drum. This method was used for somewhere between 100 and 200 feet of the tunnels on the Halava side. For the rest of the tunnels, drilling and blasting was used. Using explosives to remove rock can be a dangerous business, and it's done very carefully. At this point, the tunnel was created in sections. First, the upper section, or heading, was dug out in 3 parts. First the middle, and then both sides. Once that was done, the lower section, or bench, was removed. Again, the middle first, then the sides. To do this, the crews drilled 10 to 12-foot deep holes across the face of the area they wanted to remove. Once that was done, they inserted explosives into each hole and tamped them carefully into place. Once the explosives were all in place, they were all connected with fuse that burns very rapidly. Some of the fusing the tunnelers use can burn hundreds of feet per second. At this point, all personnel were cleared from the tunnel, and the explosives were detonated. Each explosion would loosen a section of rock about 8 feet deep. Once it was safe, workers returned and loaded the loosened rock into trucks that backed right up to the rock face. The rock dug out of the mountain to create the tunnels is called muck in the industry. For the Haiku contract, the muck was taken by truck and dumped next to Likelike Highway, forming a small hill. That muck was reused later as the base for the construction of the Kaneohe interchange. This saved millions of dollars in the cost of constructing the interchange because costly imported rock material was not required. The muck from the Halava tunneling contract was used as base, for fill, and stored for use on other H3 projects. At the end of the digging, the builders had made 2 horseshoe-shaped tunnels, 45 feet wide and 33 feet high. On average, the work went ahead at the equivalent of between 7 and 8 feet per day. But traffic won't be traveling through bare rock tunnels. A lot more had to be done before cars could be allowed through. Once the rock or dirt from the blasting was taken away by the trucks, dowels like this were inserted into the rock as anchoring for wire screen. First, holes were drilled, and then the dowels positioned. Once the screen was firmly attached to the dowels, workers sprayed a special kind of concrete called shotcrete onto the screen. Shotcrete is designed to harden quickly so that it can be applied to vertical surfaces or even overhead and will dry before it runs off. This is the first stage in reinforcing the tunnel. While the data obtained from the construction of the exploratory tunnel had given designers reassurance that high-pressure water would not be a problem in the construction of the main bores, in some areas of the tunnel, rainwater percolates down from the mountain above. This required the installation of a moisture control barrier. First, rubber patches were attached to the shotcrete. Then, workers welded 6-foot wide strips of plastic membrane, something like the lining used for swimming pools, to the patches with heat guns. When they were finished, they had a seamless barrier which guides the water from the top of the arch, down the sides, and into the tunnel drainage system. This membrane was used in areas of the tunnel where water would have caused significant problems. The workers installing the moisture barrier worked on a 50-foot long form that's basically scaffolding. This scaffolding is called a jumbo, or traveler, and was specially built at the site to fit inside the tunnel bores. The jumbo moves down the tunnel rolling on rails, just like a train or a subway, but it was moved very slowly, 50 feet at a time, whenever workers finished one section. Several jumbos were constructed for different stages of the construction process in each tunnel. After the moisture barrier was installed, workers installed rebar, this heavy steel reinforcement, as a framework for the construction of the arch. Then another rolling scaffolding, the arch jumbo, was put in place, and a form was constructed for pouring a 14-inch thick, 50-foot long section of the tunnel. Conduit for utilities was also built into the forms. When the concrete had set and the forms were removed, the jumbo was moved another 50 feet into the tunnel, and the process was repeated. After the tunnel wall was poured, precast wall panels containing air supply ducts were installed. I'll tell you more about those in a minute. The next step in the construction process involved building another jumbo, 150 feet long, for the tunnel ceiling, which was cast in place. As with the arch jumbo, this movable platform was used to assemble the wooden forms and then the rebar reinforcement. Finally, concrete was poured into the forms and allowed to set. The concrete ceiling is about 12 inches thick. It was designed with a small amount of arching so that it could support a center wall above it without the need for a central support in the tunnel. The ceiling divider, or plenum wall, is necessary for tunnel ventilation, which I'll get into shortly. On average, the contractors built the ceiling at a rate of about 50 feet a day. Previously, I mentioned the runoff of groundwater from the tunnel membrane. This water goes to one of two drainage systems constructed within the tunnels. The groundwater system leads to pipes outside the tunnels and returns the water to the area. Water that's used for cleaning the tunnels and water tracked in by vehicles is captured by another drainage system. This water can become contaminated with hydrocarbons and other byproducts of automobile exhaust and will be channeled into a system that leads to holding tanks. After the walls and ceiling were constructed, work began on the roadway itself. A pervious base was added on top of the floor of the tunnel and the drainage systems and then compacted. Next, a concrete roadway was poured that is at least 2 feet 6 inches thick. This was done in much the same manner most modern highways are built. At the same time, the safety walk beside the roadways were also built. After the walls were up and the roadway finished, the tunnels were lined with ceramic wall tile. Tile was chosen to facilitate cleaning and reflect light. These tiles absorb less light than concrete, allowing the lighting system to be designed to consume less wattage while providing adequate illumination. The darker color tiles installed near the walkway were chosen to shadow the supply air ducts and to conceal the dirt which will accumulate in that area. The lighter color tile installed near the ceiling reflects more light than the darker tiles. With proper cleaning equipment, it'll be possible to wash both tunnels in less than 2 weeks. During daylight hours, there's a severe difference in the amount of light outside and inside a tunnel. But rather than simply adding enough lighting so that the inside of the tunnel is as bright as outside, which would be very expensive, the tunnel planners designed transition light at the entrance to each tunnel. As people drive farther into the tunnel, the lighting is gradually reduced so the driver's eyes have time to adjust. This allows an overall lower level of light to be provided, with lower operating costs, while avoiding the common problem of momentary blindness. Let's talk about what else had to be done before the tunnels could open. Safety is a big factor in present-day tunnel construction. The National Fire Protection Agency has developed guidelines for monitoring the environment within tunnels and establishing minimum air quality standards. The standards necessitate sufficient ventilation to allow the egress of the public in the event of a major fire. The inclusion of ventilation fans necessitates monitoring to determine when to use the fans, operating personnel to implement their use, and maintenance personnel to assure their readiness. The two tunnels are divided into 4 sections of approximately 1/2 mile each. Each of the 4 portal buildings houses 8 fans, 4 supply and 4 exhaust, for a fully transverse ventilation system. Each fan is 84 inches in diameter. That's 7 feet from the top of the blades to the bottom. Each fan is approximately 200 horsepower, capable of moving 210,000 cubic feet of air per minute when operated at high speed. Adjustable frequency controllers are used to allow the fans to be run at a nominal half speed. Fresh air is delivered through a plenum above the tunnel ceiling and forced down to just above the roadway level through precast wall panels or flues, which I mentioned before. The panels were made outside the tunnels and then attached to the tunnel walls after the walls were poured. The top of the panel then was made a part of the ceiling, and the bottom became part of the safety walks when they were poured. So the air goes from the tunnel portal through the plenum above the ceiling and is then discharged into the tunnels through air ducts that are spaced every 5 feet along the right shoulder of each tunnel. This fresh air is swept across the roadway and pulled up into the exhaust ports located in the ceiling above the fast lane. Under normal conditions, when the northeast trade winds are present, which is on average about 50 weeks out of a year, natural ventilation creates winds of about 15 miles per hour, which blow from here at the Haiku portal through the tunnels toward the Halawa portal. The piston effect of traffic will tend to assist the natural ventilation in the Halawa-bound tunnel and tend to stall the natural ventilation in the Kaneohe-bound tunnel. How often and how much extra ventilation will be needed will depend on the trades and the traffic. What we do know is that the electricity to operate the fans won't be cheap, so every effort is going to be made to assure that ventilation fans will only be run when absolutely necessary. To accomplish this goal, carbon monoxide levels are monitored at 1,000-foot intervals. There are 20 strategically placed exhaust monitoring computers, 10 in each tunnel. The wind speed and direction in each tunnel is measured. All this data is constantly analyzed, and optimum ventilation levels and configurations are suggested to the tunnel operator by the computers. The portal buildings were designed to accommodate this massive hardware in the smallest space possible. They were also designed to reduce the visual impact of the essential portal structures.